Good day everyone, I am Irene Masienzo, STEM 11. In this video, we're going to discuss the concept of limiting reagent, which can also be called as limiting reactant. Along our way, we're going to discuss a related topic called excess reactant. Now, limiting reagent, excess reagent, this stuff all has to do with chemical reaction. But to explain this, I want to start talking about some analogies on cooking since I like cooking. We're going to compare a chemical reaction in a cooking recipe. So now we're gonna make a cheeseburger. We're gonna need a bun, a piece of cheese, and a slice of meat. So now, since we're comparing a chemistry to a cooking recipe, try to understand this. 1 bun plus 1 cheese plus 1 meat, we're gonna put that together and we can make a cheeseburger. 1 bun plus 1 cheese and a piece of meat, this stuff is called a reagent in a chemical reaction, and the cheeseburger is the product. So what is reagent? Reagent is a substance that is used to test for the presence of another substance by causing a chemical reaction with it. So let's get back to our cooking. Let's say we have a 4 bun here, nice slices of cheese, and 3 pieces of meat. So you notice that there is a different number of each one. It also happened in a chemical reaction with a different amount of each reagent. So we're talking about a limiting reagent here. So given the different numbers of each reagent, we're going to make a 3 cheeseburger since there are also 3 meats. So we conclude that a meat is a limiting reagent. So what is a limiting reagent? Here is the meaning of this. Limiting reagent is the first reagent that is used up in a reaction. When the limiting reagent is all used up, no more product can form and so the reaction will stop. So we call this as a limiting reagent because it limits how much the product we can make. It doesn't matter if we have 1,000 of cheese and 100 of buns. Once we run out of those 3 pieces of meat, the reaction will stop. So we have the product of 3 cheeseburger. So we notice that we still have 1 bun and 6 slices of cheese. And this is what we call as excess reagent. So what is excess reagent? Excess reagent is what is left over after the reaction stopped because the limiting reactant got all used up. So we have the excess. 1 excess of bun and another 6 excess of cheese. So now that we have talked about the concept behind the limiting reagent and excess reagent, let us use this information to solve some problem that is related to a chemical reaction. But before we proceed this, keep this in your mind. Limiting reagent often isn't the reaction you have the least of. Instead, it is the first reactant to run out during the reaction. So let's look for an example that uses a real chemical reaction. Here is the chemical equation. We have N2 plus 3H2 and 2NH3. So we're going to solve the problem. What is the amount of NH3 in moles that can be made with 3.2 moles of N2 and 5.4 moles of H2? So after we compute this chemical equation, we're going to determine which is the limiting reagent and which is the excess. In order to find the greatest amount of NH3 that we can make, since we're looking for it, first we should figure out which of these 2 things is the limiting reactant. We're gonna take the amount of N2 and we're gonna see how much H2 would be needed to use all amount of N2. And then we're going to take the amount of H2 and we're gonna see how much N2 would be needed to use all amount of H2. We'll start on N2 since the amount of this is 3.2 moles So we have 3.2 moles of N2. We're going to multiply 3.2 since the coefficient is 1. So we're gonna put here a 1. So the answer is the same. We have 3.2 moles since we multiply 3.2 times 1 equals 3.2 moles. Then next, we're going to multiply H2 by 3.2. We're going to multiply H2 by 3.2. Since the coefficient of H2 is 3, here it is. 3 times 3.2 is equal to 9.6 moles of H2. So this is how much we need to use all of N2. Next, we have 5.4 moles of H2 multiplied by 1 mole of N2 and 3 moles of H2. So we need to cancel this out. So 5.4 moles times 1 is equals to 5.4 moles of H2 divided by 3 is equal to 1.8 moles of N2. So as you can see, it looks like we're multiplying N2 and H2 by 1.8. 1.8 mole of N2 multiplied by 1.8 mole of N2 is equal to 3.2 moles of N2. So 5.4 moles of H2 multiplied by 1.8 moles of N2 is equal to 9.6 moles of H2. So now, let's determine which is the limiting reagent and which is the excess. We have 3.2 moles of N2 and we need to have 1.6 moles of H2. But we don't have that because the amount of H2 is just 5.4 moles of H2. So we conclude that the limiting reactant is the H2. So H2 is a limiting reagent since it is the first thing to run out and the excess is the N2. So let's start to find the greatest amount of NH3. So the limiting reactant is the H2. So we have 5.4 moles of H2 multiplied by 2 moles of NH3 over 3 moles of H2. So cancel this out. 5.4 multiplied by 2 moles over 3 is equal to 3.6 moles of NH3. This is the greatest amount of NH3 that we can form. Let's figure out how much of N2 is left over. 3.2 moles of N2, we need to subtract how much we use. We only use 1.8. So the answer is 1.4 moles of N2. This is how much are left over after the H2 run out. In general, the product that can be made is 3.6 moles of NH3 and the excess is 1.4 moles of N2 and the H2 is the limiting reactant. So now that we have talked about the limiting reagent and excess reagent, here is our another topic, mass relationship in a chemical reaction.
Lesson we're going to learn about mass relationships in chemical reactions, and we'll be able to determine what mass of a reactant will create the desired mass of a product. So to recap what we know already about stoichiometry, we know that the coefficients in a chemical equation represents the ratio of molecules, and it also represents the ratio of moles in a chemical reaction. But what about mass relationships? It's not so easy because the molar masses of different elements are very different. So you can't just mix two masses together and expect in those mole ratios and expect to have the outcome that you desire. So instead, the first thing you'll have to do is convert your masses to moles, examine the mole ratios, and then convert back to the mass for the substance that you're trying to determine. So in this example, this is taken out of our old grade 11 textbook. It states the buildup of carbon dioxide on a spaceship is a serious problem. However, scientists have found a simple way to remove it from the air. Carbon dioxide reacts with lithium hydroxide to make lithium carbonate and water. If each person on board a spaceship made 1,000 grams of carbon dioxide per day, how much lithium hydroxide is needed per day per person to deal with it? So the first thing that we'll need is the balanced chemical equation. And if we look at this equation, we can see that we have one carbon on the reactant side and one on the product side, so that one's balanced. We have 1, 2, 3 oxygens on the products or reactant side and 4 on the product side. We have 1 lithium, but 2 lithiums, and then we have 1 hydrogen and 2 hydrogens. So the first thing that I would balance would be the metal ion. So I'll put a 2 here. That's going to give me 2 lithiums. It's also going to give me 4 oxygens, which matches over here, and 2 hydrogens, which matches over here. So now our equation is balanced. The next thing that we need to do is list what information we already have. So we were given the mass of carbon dioxide. That's equal to 1,000.0 grams. We can find the molar mass of carbon dioxide. So the molar mass of CO2 is equal to 12.01 plus 2 times 16.00, the molar mass of oxygen, and that is equal to 44.01 grams per mole. And then we can find the molar mass of lithium hydroxide. That's equal to the molar mass of lithium, 6.94, plus the molar mass of oxygen, 16.00, plus the molar mass of hydrogen, 1.01. So that is equivalent to 23.95 grams per mole. So we'll use this information in our solution. So since there's many steps to solving stoichiometry problems, it's acceptable if you place your information in a chart or a table to track your work. So this table actually demonstrates how you can solve for your mass of your product in a easy to follow format. So what I did was I put the balanced chemical equation in each reactant and product or a cell in the the table, so they represent a column each. And then down the side, we have our mass, because that's what will be our starting point. The molar mass, the moles, and then whatever the coefficient ratio is in front of your column. So the way this works is you divide down. So mass divided by molar mass gives you your moles, and then you divide by the coefficient, and then to get your solution, you multiply up. So you would carry over that. If there's a coefficient here, you would multiply, then you get your moles, and then you multiply your molar mass to get your mass, and that's how you would solve this solution. And you could actually, we're being asked to find out how much lithium hydroxide is needed per day, but you could also carry that over and figure out how much lithium carbonate or water was produced as well. So first of all, we'll put the information that we've already found or been given into our table. So don't forget, we balanced this chemical equation. So there was a 2 here. We know that we have 1,000.0 grams of carbon dioxide. We know that the molar mass was 44.01 grams per mole, and that the molar mass of lithium hydroxide was 23.95 grams per mole. So now we start doing our calculation. So 1,000 grams divided by 44.01 grams per mole turns out to be 22.7 moles. There's no coefficient, so we'll divide by 1, but then we carry that over and times by 2, so we're going to multiply up. So you actually end up with 45.4 moles of lithium hydroxide. We're going to multiply that by the molar mass, and we end up with a mass of 1,090.0 grams. So every person on board the spaceship will need at least a kilogram of lithium hydroxide, so 1,090.0 grams of lithium hydroxide per day. Now, if we wanted to figure out the amount of lithium carbonate or water that was produced, we can also carry that information over. So for this one, we divided by 1. There's a coefficient of 1, so we multiply it by 1. So this would be 22.7 moles. And for this one too, there's no coefficient, so 22.7. So then we can find out the molar masses of each. So the molar mass of lithium carbonate is 73.89 grams per mole. And for water, it's 18.02 grams per mole. So if we multiply the first one by 22.7, because we multiply up, we would end up with 1,677.3 grams of lithium carbonate. And then the other one, 22.7 times 18.02, we end up with 409.05 grams of water.